Typical BeMS applications in commercial buildings, what do we use them for? I'm sure looking down the list of attendees here, you're probably quite familiar with these, but I will just go through them. We've already talked about plant enabling. You need to switch your plant on and off. With the BeMS, we obviously have time switching functionality built into that. So part of the software application is the ability to set up times that you want your plant to start and stop. We can often put in specific holiday periods, but we can also get far more advanced scheduling as well because it's software based. If you had just a time clock to switch this on and off with, you would need to go down and change everything when it's a bank holiday. With a BeMS, you can just set up an exception date, and when it's a bank holiday, then none of your plant comes on. We can also bring in other variables for our plant enable and disable as well. You might have heard the phrase optimized start-stop. With optimized start-stop, we use outside air temperature or weather data so that we can make sure we reduce our energy consumption. The idea being that if you want your plant to be at temperature at 8 o'clock in the morning, you might set your boiler to come on at 4 o'clock in the morning, so it's got plenty of time to heat up. But as the weather starts to get warmer, so we're in spring, it's still a little bit chilly, so we want our boilers to come on, but they start at 4 o'clock in the morning. It's warm, the whole system is warmed up by 6 in the morning, so for 2 hours we're heating an empty building. And the idea of an optimized start-stop is it looks at the outside air temperature, or in some systems the weather data, and it will start the plant at the last possible moment so that it reaches temperature at 8 o'clock in the morning, and we can save energy that way. We can also do a stop procedure as well. A building takes time to cool down. It's more unusual to use optimized stop because it can provide problems, particularly with the random working patterns that people have in modern buildings. But optimized start is implemented on a vast majority of buildings. We can also save energy by using occupancy sensing. So we have our plant enabled in a standby mode, and we don't set it up to operate properly until an occupancy detector, when you walk into a room, either connected to a lighting system or directly to your BeMS, senses that there's an actual person in the room. And we can integrate with other systems. Something we used to do when I was working doing BeMS for retail was that the BeMS would be tied in with the security system. So they would need all of the plant running until the last person left. So they would set the alarm at night, and the alarm came on, and then that would shut all the plant down. So we can integrate with other systems for our plant enable. We can also use our BeMS for plant rotation. Duty standby changeover means that if we have redundant plant, i.e. or a twin-headed pump, as is shown in this drawing here, we can rotate that plant so that we can give it even wear, or we can have one designated as the duty pump, and we can run that, and then if it fails, we can switch over to the standby pump. We can also have lead lag operation. Lead lag is slightly different from duty standby. Boilers and chillers need to be sequenced. If you've got, as is shown in the drawing here, 3 boilers, you would want to sequence them on based on the demand in your building. You don't want to just bring them all on. So we can use our BeMS to sequence those on. But we can also use that to change which boiler is the lead boiler. If you just had number 1 as the lead boiler all the time, it would get much more wear and tear than boiler number 3. So we can actually change so that every week we have a different lead boiler so that we get even wear across all of our boilers. We can also use our BeMS to do a seasonal changeover. It used to be referred to as summer winter. If you go into some very old plant rooms, you'll see a switch on the front of the control panel. It'll say summer and winter, and this enables and disables various plant depending on your season. Obviously, we can do that now based on outside air temperature, internal air conditions, whatever we need to, so we can provide seasonal changeover. Temperature applications are probably the biggest application that we see within BeMS. I don't think it's too much of an exaggeration to say that. We control temperature for a number of reasons. Comfort of occupants is a very normal reason for controlling temperature. Most people are comfortable within a temperature range of about 20 to 24 degrees C. Somewhere in the middle, 22 is about the spot for that. Don't get too obsessed about it. Different people feel temperature in different ways. You can't do anything about personal preference, but if you keep it within those bounds, then most people will be comfortable. We also use temperature control for asset protection. As already mentioned, in data centers, you've got equipment such as computers producing large quantities of heat. You need to remove that heat. So we use a temperature control application in order to keep that environment. Used to be, when I started doing this, cold, but these days it's cooler. So although data centers operate at much higher temperatures, they still need to have the heat removed. And we also have to think about frost protection, which is a temperature control application. Water, unlike most things, expands as it freezes. If you imagine a tray of ice cubes, you put them in the fridge. When you put them in, the water is level. When you take them out, you've got little domes of ice because the ice has expanded. If that ice is in pipes in your systems, then that expansion can cause the pipes to rupture. So we look at outside air temperature, we look at various temperatures of the water going through the building, and we operate our plant to protect against those freeze events. We also look at internal air temperature. We have to prevent condensation forming within buildings. Sometimes it's called night setback or stage 3 frost protection. But if we allow our buildings to get too cold at night, as an example, you will get condensation forming on the windows. This can run down the windows and it can damage carpets. If you've got wooden frames, etc., it will damage those. So we want to avoid condensation as well. And we do that by controlling the temperature in the space. For temperature sensors, I've actually put in a couple of temperature sensor types. I haven't done this for every application because there's lots of different types of temperature sensors out there. The first thing you have to do when you're selecting a temperature sensor is obviously choose the correct application: space, duct, and immersion. And of those duct and immersion sensors, you need to be acutely aware that whilst they can often look the same on the outside, they are not always the same on the inside. Duct and immersion sensors have a long probe on them. Immersion sensors tend to have that probe filled with a potting compound. What this means is that if you use an immersion sensor in a chilled water system, then condensation can't form inside the sensor itself, causing damage to the sensing element. Duct sensors don't always have those, so the two are not necessarily interchangeable. We have different types of signals that we get from our sensors. We have passive temperature sensors, which are typically a lower cost option. Thermistors or RTDs, resistance temperature detectors. Again, don't want to dwell on what all these things are. I need to leave some surprises for those of you who are going to come on the BCM 01 course. But they are a lower cost option. They have a non-linear response though, which means that the further away you get from the center of the curve, if you look at that little drawing down on the bottom right-hand side, we see a flattening of the curve or a steepness of the curve as we move away from that center point. So we need to characterize these sensors. We have active temperature sensors, which will give out 0 to 10 volt DC based on a temperature range of 4 to 20 milliamp. And we also must not forget these smart temperature sensors. A lossless digital bus signal. It's very important that we don't have to account for changes in resistance of the cable. We don't have to account for voltage drop in the cable. And those smart sensors will typically work over Modbus or BACnet MSTP. Sorry, BACnet MSTP, I don't think I've covered that in here. That's master slave token passing, but that's the version that goes on RS485. And we also control humidity within spaces, again, for the comfort of occupants. A lot of people, and particularly I see this over and over again with maintenance teams, they are tasked with controlling the temperature at 22 degrees C and nothing else. But people's comfort is also affected by humidity. We feel comfortable when the relative humidity is between 40 and 60%. And we also start to feel uncomfortable if absolute humidity, that is the actual amount of moisture in the air, goes above 11 grams of moisture per kilogram of air. So humidity has a bearing on our comfort. If your room is at 22 degrees C, but your relative humidity has dropped down to about 30%, you are still going to have people who feel uncomfortable. That level of humidity is quite possible to happen in the winter. You provide a lot of heating, it drops the relative humidity as a result. People get itchy eyes, sore throats. If you have conditions such as eczema, it will exacerbate those as well. So we need to be mindful of controlling humidity. One thing I would say is in the UK, we have pretty consistent humidity year round. So relative humidity problems tend not to be an issue. But you need to take it into account. Just because it's 22 degrees C in your space, if people are complaining that they don't feel comfortable, it's no good saying, well, you're at 22 degrees C. You do need to look at other factors. And humidity, relative humidity, is a particular factor that you would need to want to look at in those circumstances. Again, those of you doing data centers, humidity has an effect on static discharge. So if you've got a buildup of static electricity and you have very low relative humidity levels, then static discharge is more likely. Static discharge can damage circuits. And so if you have static discharge within a data center, what you can do is damage the computers, and that can obviously have some quite damaging implications. So in data centers, oddly, we tend to find a need to humidify the space, to actually add humidity to the space in order to make sure that we don't promote that static discharge. The humidity itself is not what causes the static discharge, but if you get a buildup of static electricity, it is more likely to arc if you have low relative humidity. And we also use humidity sensors for dew point sensing control. I won't go into the ins and outs of it now, but if you have a chilled beam in your room, it doesn't have a drip tray. So if it gets too cold, then you can get condensation forming on it. And this is all to do with the dew point temperature. So we need to know how much moisture is in the air and at what temperature that air is, so that we can find out what the dew point is and avoid our chill beams being at that dew point temperature, lest it should rain indoors. CO2 sensing and air quality, so the quality of the air in our buildings. I have got just a little further example in the next slide here, but carbon dioxide is a good indicator of how many people are in a building. If we are controlling the ventilation properly, then we should see a parts per million value of CO2 in the space of around about 1,000. So there should be 1,000 parts CO2 per million of air. That varies depending on the application. You probably could get away with 1,500, although people will start yawning. If you're doing schools, then people are asking now for 750 parts per million. So there's more fresh air and less CO2. But 1,000 parts per million is a fairly established center point for this. Air quality sensing is slightly different. Air quality sensing measures the level of volatile organic compounds in the air, which sound pretty hideous, particularly in these strange days. But VOCs, all VOCs are any substance which is gaseous at room temperature. So this can be things like cleaning fluids. If someone paints a wall, it will give off VOCs, volatile organic compounds. people emit volatile organic compounds. I once shared a hotel room with my brother. He emits an enormous amount of volatile organic compounds. These VOCs tend to not lead too much to ill health, but they can cause headaches and dizziness. But we do need to treat air quality and CO2 sensing in a slightly different way. So the CO2 sensing, the reason that we control it is obviously for the comfort of the occupants. People need approximately 10 litres per second per person of fresh air in an office environment. That's how much air we have to bring in. That's the CIBSE recommended requirement. Because we exhale CO2 at a steady rate, so we all breathe in oxygen, we breathe out CO2. By measuring that concentration in the space, we can see whether the space is adequately ventilated. Now, the example, or a classic example of this, is probably more relevant now than it ever has been. If you design a space for 100 occupants, you need to provide 10 litres per second per person of fresh air for those occupants. So 10 times 100 is 1,000 litres per second. That's what your ventilation plant needs to achieve. Right now, that office may be personed by just 10 people instead of 100 people. And so instead of providing 1,000 litres per second, we actually, if we've only got 10 people in there, we only need 100 litres per second of air in there. If we didn't have any means of establishing the occupancy, then we would be over ventilating the space. Now, that's great for the occupants, a lot of fresh air, but you're going to use a lot of fan energy to provide that. So by measuring the CO2 levels in the space, we can ascertain roughly how many people are in the space, and we can slow the fan down accordingly. And again, don't want to dwell on exactly how they work, but if you slow a fan down, then you use far less energy than if it is running at full speed, and it is not a linear relationship. Slowing a fan down to half speed will actually, slowing a fan down by 20% will actually use about half the energy that it was before. So it's important to do this, and it's one of the reasons we see so many CO2 sensing applications these days. We sense differential air pressure. There's a number of reasons we do that. One is to control fan speed, but another one is to actually measure airflow. We can use velocity probes to measure static pressure, total pressure, and we can ascertain volumetric airflow from those. Again, quite an advanced concept, so way beyond the scope of this hour and a half long session. We also measure liquid pressure, which will give us information on things such as leak detection. We can have pressure alarms, and we can also control the pressurization of systems such as low temperature hot water or chilled water systems using single point liquid pressure sensing. Now, with air pressure sensing, you always have differential air pressure sensors. If you only want a single point, you leave one of the probes open to atmospheric pressure. With liquid, we have single point, but we also have differential liquid pressure sensing as well. Differential pressure sensing is used very, very extensively for pump speed control. Again, without going into huge amounts of details about how systems operate, if we can maintain a constant differential pressure across a pump, then we can minimize the energy consumption of that pump. The one shown in the drawing here is quite a small pump, so we're only going to realize small energy savings. But if we have a much larger system with maybe sort of 20, 30 kilowatt pumps on it, then obviously that is going to offer us some significant energy saving benefits. And we can also use differential pressure sensors. If you look down in the bottom right-hand corner, there's a thing that's called an orifice plate. By creating a restriction in the pipework, we can use a differential pressure sensor to measure volumetric flow.